Hello and welcome to the first lesson in this course on metric spaces and topological spaces. Linked in the description is a booklet which you can download, print off and fill in as we go, which will make following along with the video easier. It also contains the questions and examples we will go through in the video and also homework questions, and I'll also put a link to the solutions. Okay, a quick overview of where this course will take us. So the first part is going to be basic set theory. This is mainly aimed at people who aren't studying a formal maths course, so maybe you're a physicist or an engineer and you want to try some pure maths. So this part of the course will cover things like what is a set, functions between sets, things like that. Maybe if you're a maths major or you're studying a maths degree, maybe this first part of the course will be things you know. Then the second part of the course will be on metric spaces. And then finally, the third part is on topological spaces, and this will be the biggest part of the course. Now, all the references, textbooks, course notes I find that are useful, and we're basing this course off, I'll put in the description, so you can find those. Also in the booklet, I'll explicitly recommend particular chapters relevant for that lesson. So, what is a set? A set is an unordered list or collection of unique objects or elements. So a nice analogy is just a box with things in it. So a set is the box and all the objects or elements are in the box, and it doesn't matter what order you put them in or take them out. And the elements of the set, so the things in the set, could be any mathematical object. They could be numbers, letters, other sets, shapes, coordinates, functions, huge range of different things. And we can define a set by just listing the elements. So for example, if we have the set A, this is just a set of 1, 3, 2, 5. And we define the set with the curly brackets. Everything inside the curly brackets is what's in the set. And because this is unordered, we could have written those numbers in any order. So we could have had 1, 2, 5, 3. It would be the exact same set. And also notice all those elements are different. So there's no repeats. A different example of a set is this set B. And now this set contains 4 elements. So the first 3 elements are the letters C, M, N. But then the fourth element is another set, and that's just the set that contains A and B. Then finally, we have another set, C, and this contains 2 elements, and those 2 elements are the set A and the set B. And we can write that out in full, and you see we have a set, and in that there is the sets A and B, and in B there is another set, AB, so they can stack. Alternatively, we could define a set by using a rule. So here's an example. We could define the set D, and D is all numbers x such that x is prime, where the colon means such that, so it tells us a rule is coming. Alternatively, we could have the set E, and E is the set x such that x squared plus 2x equals 0. There are 2 solutions to this equation, so this set would just be equivalent to 0 minus 2. Now this set's a bit more complicated. This set F is the set of coordinates x, y, such that y is equal to x squared and, so the comma means and, so and x is even. So it would contain things like x equals 2, y equals 4, but it wouldn't contain 1, 1, or because x isn't even, or 1, 7, because 1, 7 doesn't obey y equals x squared. Okay, so let's look at some common examples of sets and sets that come up in lots of situations. The first one is the empty set, and that's given by this character here. It's like a 0 or an O with a slash through it. And this is just a set with nothing in it. Another common type of set are intervals of the real line, so just intervals of numbers. So here, if they're normal brackets, then it's an open interval, and that means the ends, so the values a and b, are not included, and you can see that from the inequality signs. We have closed intervals, and here the square brackets mean a and b are included in the set. Or you can have sets that are neither open or closed, or one side is open, one side is closed. And again, you can see that from the inequality signs. Or here a set which goes from A all the way up to infinity. So we'll see lots of examples include intervals, so it's good to have this notation written down and memorized. The other useful sets probably seen before are n, which is the natural numbers, z, which are the integers, q, the rational numbers, r, the reals, and c, the complex numbers. These are all just sets that we'll see time and time again, so they have shorthands. Something is an element of a set if it is in that set. And to express this, we would say P, and then this symbol that maybe looks like a backwards 3 means in, or is an element of. So we use this symbol to say that P is in A, or is an element of A. Or we can cross it out to say that P is not in A, or is not an element of A. So as an example, 4 is in the set of even numbers. And the point, or the coordinate, 1, 7, is not in the set where of y equals x squared and x is even. For two reasons. 1, x is not even, and 2, 7 is not equal to 1 squared. So 1, 7 is not in that set. Here's a trickier example, and 2 is not in this set. However, the set containing 2 is in this set. So it's just a bit of a nuance between an element and a set that only contains that element. On this slide, I'm just going to ask some true or false questions, and then you can pause the video, think about the answer, and then I'll explain it. There isn't space to write this down on your booklet. They shouldn't really take any kind of working out. You just have to think them through. So for the first one, is M an element of A? This is false. M is not an element of A. A just is 1, 3, 2, 5. But M is an element of B. The second one is AB, or the set containing AB, an element of B. This is true. And we can see it's the last element of B there. Is 0 in the empty set? This is false. Nothing is contained within the empty set. So no matter what was there, this would be false. Then is 3 an element of the open interval 3, 4? And this is no, because the open interval, those normal brackets, mean we just use the greater than and less than signs. So 3 is not included in that interval. For the next one, is 3 included in this interval 3, 4? This is true, because the square brackets means we do include that value. So 3 is included, but 4 would not be. And finally, is 2 an element of this set? This statement is true because 2 squared does equal 4, so it does obey the rule. So when are two sets equal? So we'd say that two sets A and B are equal if they have all of the same elements. And remember that things are unordered, and we say that every element's unique. So it doesn't matter if the elements are in the same order, because there is no order. And if one set has, or appears to have, multiple copies of the same element, well, we just don't count them. So what really matters is they have the same unique elements. We could write this in a formal mathematical notation by saying A equals B. Then the IFF means if and only if then the upside down A means for all. So this is A equals B if and only if for all elements P in A, then P is in B. And for all elements P in B, then P is also in A. Or A equals B if and only if all the elements of A are in B and all the elements of B are in A. These three lines are entirely equivalent with different levels of formality, but they all mean exactly the same thing. And we'll see a technique to work out if two sets are equal in a minute. In short, a subset is just a set that's fully contained within another set. So we'd say a set A is a subset of a set B, and it's written with this subset symbol. It looks a bit like the less than symbol. So we'd say this if all the elements of A are also in B. And alternatively, we would call B the superset of A. And this is written the other way around. Or we can rewrite this using our formal maths notation. We'd say A is a subset of B if and only if for all P in A, so all elements in A, then P is also in B. So as an example, the set containing 1, 2, and 3 is a subset of the integers. So they're all integers. Cm is a subset of this set because C and M are both in that bigger set, that superset. And now the set containing AB is also a subset of this because there's one element of that set, which is the set containing AB, and the set containing AB is in that superset. The empty set is a subset of anything. Because there are no elements in the empty set, then this definition is automatically true. Because there's no elements, all of those elements are automatically in anything else because there's none of them. It can be a bit weird, but the empty set is a subset of anything, or any other set. And A is a subset of itself because every element in A is also in A. Another useful set is called the power set, and this is the set of all subsets. And we can write this either P of A, or some people write it as 2 to the power A. And so, as an example of a power set, if we take A to equal 1, 2, 3, then the power set is the set of all subsets. So you see we have the empty set, because that is a subset of A. We have all the subsets that just contain a single element, all the subsets that contain 2 elements, and finally we have A itself, or the subset that contains all the elements. We can use this idea of a subset to aid in proving if two sets are equal. So two sets, A and B, are equal if A is a subset of B and B is a subset of A. So if we can show both of these, then that's the same as the two sets being equal. And some books will use this as the definition of two sets being equal. So let's look at an example. We've got two sets here. From the outset, they look very different, but we'll show that they are actually equal. So we need to do this in 2 stages. Firstly, we need to show A is a subset of B. So to do that, we need to show that each element of A obeys the rule that defines B. So let's check 2. That does obey the rule, therefore 2 is in B. Let's check 3. That obeys the rule, so 3 is in B. 4 obeys the rule, so 4 is in B. And then we can show that B is a subset of A. So we can do this by taking our equation, factorizing it, and then we see that the solutions are 2, 3, and 4, and therefore, and we know that all of these are in A. So therefore, B is a subset of A. We've got some more true or false questions. As before, there isn't any space in the booklet for these. They should be quite quick. You should just be able to think about them. When I go through them, pause the video, think about it, then come back and I'll put up the answer, or explain the answer. So firstly, is the set containing little a, little b, is this a subset of big B? This is false, even though the set with little a, little b is an element of the set big B. In order to see if something is a subset, we need to check each of the elements individually. So, is little a in the set big B? No, and nor is little b. What is an element of big B is the set containing a and b, but the elements little a and little b are not in B themselves. For the next one, is the open interval 2, 3 a subset of the closed interval? This one is true. That's because the closed interval contains the points 2 and 3 and everything in between. The open interval is just everything in between. Okay, is this true? This is true because in order for x squared to equal 9, x must be plus or minus 3, but for 2x to equal 4, x must be 2. So nothing obeys both of those conditions at once. Again, this one is true. So for x to equal, or for x squared to equal 4, x must be 2 or minus 2. They're the only two possibilities. Is C, the set given above, is this a subset of Z? This is true because every prime number is an integer. For the next one, is A an element of the power set of A? So this is true. The power set, or the elements of the power set of A, are all the subsets of A, and A itself is a subset of A. And finally, is A a subset of the power set of A? This one is false. Even though it might look true, the elements of A are not elements of the power set of A, even though a subset containing just a single element of A is in the power set of A, the elements themselves are not in the power set. We're now going to look at set operations. So this is things you can do with sets. Our first operation is the union. So when we union set, we take every element that is either in A or in B. So it could be in one or the other or in both. And that's shown here with a Venn diagram. You see it's anything that's in A or in B or in both. So as an example, the set 1, 2, 3 union with the set defined by x squared equals 1 is going to be minus 1, 1, 2, 3. So that's any number that's in the first set or that satisfies the second rule. And this is equivalent to OR if we're talking about logical operations or probability questions. Our second set operation is the intersection. So this contains all the elements that are both in A and B. And it's here with the Venn diagram. You see it's just that crossover in the middle. So as an example, 1, 2, 3 intersected with the set of points that satisfy that equation is just the point 1. So minus 1 isn't included because it's not in the first set, and 2 and 3 are not included because they don't solve that equation. And if two sets have no intersection, so that is if the intersection is empty, we call them disjoint. And in Venn diagrams, this would be two circles that just don't touch each other. And finally, we have what's called the complement. So this is written A backslash B, or sometimes A take away B. And this is all the points in A that are not in B. So as a Venn diagram, you see it's everything in A, but we've rubbed out everything that's in B. So we've taken out that middle section. So as an example, 1, 2, 3 complement the set of points that solve that equation is just 2 and 3. So 1 has been taken out because it's in that second set. Obviously, -1 was never included in that first set to begin with. Okay, so now you have a chance to calculate some examples, and there is space for you to do this in your booklet. And then once you've had a go, I can put up the answers. So the first one is A complement B. The answer to this is here. It's all the elements of A that are not in B. Then the next one is B intersect C. And the answer to this is just the set containing 2. So there's only 2 is in both. And even though it's a single element, we still keep the set brackets, the curly brackets around it. And then finally, okay, I'm going to show this in 2 steps. So firstly, I'm going to do C union D. And so C union D is given on the right there. And then I'm going to do B, complement that. So I have 3 and 5. The next couple of examples, we're going to be looking at proofs of certain properties of these operations. And particularly if you're not a math student, you may not have seen proofs before, but you should still be able to have a go. So for the first example, we want to prove that A intersect B is in A, or is a subset of A. So this is equivalent to showing that if X is in A intersect B, then X is in A. By definition, if X is in the intersection, then X is in A and X is in B. Therefore, if X is in A and B, then X is in A. And now because this is true, X was arbitrary, so this was true of any X in A and B, then the argument holds for all X in A and B, and the result is proved generally. Okay, for the next example, have a go in your booklet and then come back to the video and I'll show you the solution. Okay, so now you've had a go. We want to show that if X is in A, then X is in A or B. By definition, if X is in A or if X is in B, then X is in A or B. Therefore, if X is in A, then X is in the union. We've got a couple more proof examples. If you're confident with proofs, by all means, pause the video and have a go by yourself. If you're not that confident, I'll go through the first one fully, and then I'll put up another example. So, in order to prove that A complement B intersect B is the empty set, so that means there's no elements in this. Firstly, we're going to start off by using the definition of the intersection. So the intersection here, so any point in this intersection has to be in B, and it has to be in A and not in B. So A complement B. Then we can expand this A complement B, and we can use the rule that defines that. So in order for X to be in this set, X has to be in B, X has to be in A, and X has to be in not B. So those last two come from the complement. But here, the first rule and the third rule are incompatible. Nothing can satisfy both of those. Since nothing can satisfy all 3 rules, that set is empty. Okay, here's the next example. Have a go on your own first, and then come back to the video and I'll go through it. Okay, now you've had a go. Firstly, we use a definition of the complement. So here, X must be in B and X must not be in A. Then, because they're subsets of U, introducing that X is in U is automatically satisfied for X if X is in B, because everything in B is already in U. So that second condition is automatically satisfied and therefore doesn't change what our set is. And here we have, it has to be in B, and it has to be in U, and it has to be in not A. So therefore, those last two conditions are just the definition of the complement again. Now we've got some algebraic rules that these operations obey. So firstly, there's the idempotent laws. So that means anything union itself or anything intersect itself is just itself. Secondly, there's the associative law. So it doesn't matter which order we do intersections, and it doesn't matter which order we do unions. Similarly, there's a commutative law. So again, it doesn't matter whether we do A intersect B or B intersect A, and it doesn't matter if we do A union B or B union A. And then we also have two distributive laws. So firstly, the union distributes over an intersection, and an intersection distributes over a union. All these rules are maybe what you'd expect. You can verify them or kind of justify them by thinking of the intersection as and the union as or, and seeing how these kind of follow from the way logic works. Or you could maybe draw Venn diagrams to kind of justify this. Or there's some example sets at the bottom. If you want to, you can pause the video and just verify the left and the right hand side are equal if you use these sets. Here we have even more laws of algebra. So firstly, we have the identity laws. And then the identity laws for the union. I'll give you some time to copy these down and have a little think about them. And then we also have the complement laws. I'll give you a few seconds to copy these down and try and interpret them. If you need to pause the video, obviously that's fine. Then you can verify these explicitly by using U equals 1 to 10 and A equals 2, 3, 5, 7. And then note that the complement is not associative. So if we ever see something intersected or union a complement, we will always take the complement to happen first. Some books, some notes will use a slightly different notation for the complement that will make it slightly obvious or more obvious that you want to do the complement first. But also this is a convention, and so this is just what we're going to take for the time being. Now we've got two more laws. These ones are a bit more complicated, and they're called De Morgan's laws. I'm going to show both laws to begin with, and there's space in your booklet for each of the laws, and then space underneath for proofs. So I'm going to put up both the laws, and then we'll go through the proofs of them. So firstly, we have the first De Morgan's law, and then we have the next De Morgan's law. Okay, I'm now going to go through the proof of the first one. So if we start off with U complement A union B, this is the set of points such that X is in U and X is not in A union B. So this means that X is in U and X is not in A and X is not in B. Then for this line, all I've done is rewrite that first condition twice. This changes nothing because if X is in U, X is in U. It doesn't change anything. But now we can group the first and second condition and the third and fourth condition, and we get our law. Okay, have a go at the second law and proving that yourself. Then come back to the video and I'll go through the proof. Okay, now you've had a go, I'll go through it. So, U complement A intersect B. So this means X is in U and X is not in the intersection. So this means that X is in U and X is not in A or B. So it can't be an either A or B. And then we can move the x's in U and we can combine those rules. Again, here there's no formal rule to move those around. I'm just thinking it through. So if x is in U and not in A, that's the first one. Or it could be the case that x is in U but not in B. And then finally, that first bracket is the first complement, that second bracket is the second complement. We can use these laws to evaluate this long, complicated string of unions and complements. So firstly, we can use De Morgan's laws to turn that complement and split it up and turn the union into an intersection. And here it gets important that the complement is happening before the intersection. So if in doubt, put brackets around the complements. Then we can use the complement laws to simplify that U complement B. And now we've simplified this whole chunk on the right, we can substitute it back in. And now we've simplified our result a little bit. Now we've got a union outside a bracket and an intersection inside a bracket. So we can use our distributive law. Then on that rightmost bracket, we can simplify that just to U. And then finally, if we have any set intersected with a superset, we just get back to the original set. Okay, have a go at this one on your own, and then I'll put the solution up. Okay, now you've had a go. Here is the solution, and it simplifies to A intersect B. So we saw quite a lot in that lesson, and we really help you understand and remember. If you go back and verify explicitly lots of the rules of set operations we went through, try and read through the proofs and really understand how I went from one line to the next. And of course, going through your booklet and doing the homework problems. I will link solutions to them in the description.